Hey, good morning, everybody. I am Kohta Ueno with Building Science Corporation, and I'm going to be spending a bit of time talking today about some of the tools and tricks and techniques that I use for my day-to-day work in building diagnostics. So, by the way of a little bit of introduction, I'm Kohta with Building Science. That is Joe Stiebrick's company. I've had the honor and pleasure of having Joe as my mentor and boss since 1998. Fantastic amount of information. So a good chunk of our day work and how BSC kind of made our bones is a lot of forensic examinations, delving into the bowels of screwed up buildings. You know, we're talking the weird stuff, not just water leaks. You know, freezer warehouse in Florida where we got icicles leaking out of the roof. Rich dude's house in Texas where, you know, he can't control the relative humidity for his fancy art collection. Or an airport control tower 20 stories tall that's leaking water. Those are the kind of things we do a lot of the time. So what I'm going to be talking about is my forensic work kit. Basically, you know, the key thing is looking at the building, figuring out what's going on, but there's information beyond what you can see that's pretty critical. This is what works for me. Maybe there's something in there useful for you. And I am definitely indebted to all these practitioners that I've worked with that have been happy to share the knowledge and the techniques that they've used. So a little bit of housekeeping. Feel free to take pictures of whatever slides you want to, but we're going to post a PDF of this slide deck on our website. And you know, if you're wondering about what is that piece of equipment, you know, there's going to be a list of all of those different instruments that I'm showing up on the screen. I think we're going to be slammed for time, but I'm happy to take questions when I'm standing around after the show. So the overall structure that we're going to be talking about today is breaking down these things that we're measuring that we can't see: air, water, and heat, and also in various combinations: air and water, heat and water, all of those kind of combinations, and a little bit, if we have time, to talk about how you would organize a field investigation, this type of forensic work. So let's start off with a little bit on air. This is not intended as blower door 101. Lots of other folks can do that far better than I do. Basically, all those resources that are out there on the web, from RetroTech, from Energy Conservatory, boatloads of instructional videos. But what I'm trying to talk about is beyond just doing a straight up blower door test. Here are some of the little bits and pieces that could be useful in trying to sleuth out what's going on inside a building. So let's just take an example of, so you start off with a blower door test. A very useful thing you can do is start to measure the pressure difference or the pressure drop across various parts of the shell. So here's an example. You got a standard vented attic. That pink line shows where the outside shell is. You're doing a blower door test. Depressurizing, you're doing 50 pascals across the shell. So if this is a perfectly sealed condition where the attic is fully vented and you have a completely airtight lid across the top, you would get that same difference, 50 pascals, 0, across the lid. Basically, the attic is well vented and it's essentially outside. Flip that on its head and say you're doing instead a unvented attic, spray foam up at the roof line, so basically that attic is inside. If that was all working correctly and you basically had that attic completely included within the space, if you once again measured across that ceiling, you would be measuring 0 pascals ideally. If the attic is completely inside, it's also running at the same minus 50. But in reality, what you typically end up seeing is that you're going to get some degree of difference, pressure drop across that ceiling in a unvented attic example. So what I'm seeing here in this teaching example, 25 pascals across the ceiling. That means that the attic is running at minus 25. I would say that means the attic is halfway inside, halfway outside. Or in other words, the area of the holes from the inside across the ceiling to that attic are the same as from the attic to the outside. So Here's an example of how I would use that in a forensic investigation. This is that case where the humidity control was terrible in this house in Florida, in Texas. We put some cardboard over the fireplace just so we're not blowing soot all over the place when we run the blower door. Then we realized, oh, we should probably figure out, are these fireplaces a bad contributor to the problem? Run the blower door test, measure the pressure across that, and basically you can see that the fireplace box spaces are essentially outside. A lot of leakage through that damper. That's where a lot of that outside air problem is coming from. Come on. You can also measure indoor to outdoor pressure differences. That's useful for figuring out, for instance, we've had cases where mechanical systems are massively pressurizing or depressurizing your house, resulting in problems like dust streaking or other things where outside air is getting sucked in. So basically you can set up a pressure reading inside to outside and then turn on and off the various pieces of mechanical equipment. The giant super sucker kitchen exhaust fan, the makeup air, see how well that works, all those combinations. On top of that, we probably all know with basic building science, stack effect, warm air wants to rise out of the top of the building. So you can measure that directly with a manometer, sticking that out a window up at the top. Just as a for instance, stack effect gets worse as the building gets taller. So you go to a New York City multi-story building, middle of winter, you're going to be measuring a massive pressure across the top of that and just ejecting massive amounts of air plus replacement air getting sucked in at the bottom of the building. That could be a source of a lot of issues. If you need to get more in detail with these types of pressure measurements, what you can do is a lot of the time hook up your pressure meter to a computer and you can log that pressure over time. Basically, it provides a running graph of what's going on. So that's incredibly useful for if you're looking for small pressure differences and say it's a windy day. It kind of keeps you honest. You can look at the pressure graph and say, like, does turning the fans on and off actually change things, or am I just looking at what the wind is doing here? Also, if you're doing super fancy multi-blower door tests in a building, this is the go-to control system to use. Going in the opposite direction, going from big to small, there are a lot of cases when you can use just a small duct blaster fan to measure air tightness. For instance, multifamily units, small houses, super airtight. If you're doing any passive house work, instead of lugging around the entire blower door, you can just switch to a little duct blaster, and often that'll give you enough air to solve the problem. One key thing, though, that I'd suggest if you're doing something like going down a bunch of different units in a multifamily building or a hotel, you can get screwy results if you're just taking the air from your apartment unit, ejecting it to the hallway, because you're pressurizing the hallway the same way that same time you're depressurizing your unit. So what I'd suggest is, pop open the window at the end of the hallway just to relieve that pressure so you're not getting screwed up readings. So how would I use that in practice? Here's an example of an academic pool building. Upstate New York, climate zone 6. They actually did a massive renovation project. They basically ripped everything down to the structure, did a complete reclad, new air water vapor control layer, insulation, brick. And the first winter that it started operating, they're getting all of this white mineral efflorescence staining all over the outside of the building. What the heck is going on? So they provided me with some construction photos. The walls, yeah, they look really good. They basically stripped it down to the block structure, put on a vapor closed air water vapor barrier. Looks really continuous. It's pretty obvious how to inspect it. Then a layer of foam insulation with those brick pintles, airspace brick on the outside. This is the perfect wall. This is exactly how you want to build something high risk like a swimming pool in a cold climate. Then looking at their photos of the roof, come on, there we go. They did a great job of that too. They stripped it down to the structure, peel and stick, air vapor barrier, super airtight, easy to inspect, piled up the insulation on top of that, roof membrane. That's a darn good roof assembly. So how did things manage to go wrong? We pulled out the blower door, and what we ended up doing that convinced things is we pressurized the pool with the blower door fan, basically pulling in outside air so that it pushes inside humid air out of the shell. And what they did is they got the man lift out, they busted open a part of the brick veneer up at the top of the building, and you can see that, there's the foam insulation that should be on that wall. That last photo is looking up into the cavity. You can see the foam on one side and the brick white on the other. That's the underside of the roof membrane. That's, basically, good water control detail. They got the parapet right. Peel back a little bit of foam, and I can stick my fingers into the top of that block wall. So basically they did a great job on the wall air barrier, a great job on the roof air barrier. Where the two of them met up, something happens, and apparently not much good happened. The architect was not really convinced, saying like, no, there's no way that that's actually connected. So that's when the blower door came in handy. Pressurize the pool. We're standing up there on the man lift, and we're smelling humid, chlorine-laden air coming out of that hole. Yep, there's a hole there. That's what's happening. Hot, humid air is leaking out of the pool, stack effect, rising to the top, leaks out from those air leaks, condenses on the backside of the cold brick. The water wants to leak out, carries that mineral, dry out, carries those minerals, and that's why they were having efflorescence every winter. Changing gears a little bit, another thing that's super handy for air work is a hot wire anemometer. It basically gives you a measurement of air leakage flow in feet per minute, as well as the temperature. So a lot of the time, it's really hard to demonstrate that an air leak is happening in a picture. With smoke, toilet paper, you need a video. So what you do is you hold up the meter and you're showing like, look, I'm developing all of this airflow. It's cold air. Obviously, it is outside air. Just something that is more convincing when you need to convey this information in a report or similar. Also, the probe telescopes upwards so you can look for air leaks up near the ceiling. There's a whole world of HVAC airflow measurement that I can't really get into. It ranges from bolometers on the fancy end to something more basic like an energy conservatory exhaust box, just basically measures exhaust fan airflows, to something like toilet paper, just to show like, hey, does the toilet paper stick to the exhaust fan? Good flow, bad flow. There's some useful information there. So moving on to the next topic, moving from air onto heat. So I'm going to talk first in this section about infrared cameras. So once again, this is not infrared thermography 101. This is kind of the applied version of the course. So what I'm looking for in a lot of these investigations are thermal anomalies, which is the fancy name for hot spots and cold spots. And a lot of the time you can't really, there's a lot of interpretation that needs to happen when you look at an infrared shot. Could it be an air leak? Yup. Could it be a water leak? Yup. Could it be a heat source, thermal bridge, solar gain? All of these things are on the list. This is a dumb example where I was trying to figure out what are those thermal anomalies on the floor. Obviously, you can see that that's where the sun's been shining through the window, lighting up the floor, but it screws you up when the sun goes behind a cloud and you're not seeing it and going, wait, what's going on there? So most of the time you cannot see air leaks from the outside, but every once in a while you get such an egregious case that you actually can. So cold day, brick veneer building, overcast skies, so the sun's not shining. You can see the way that there's the cold brick on the outside, and there are these stripes of warm surfaces at the face of the brick. And basically, this is an air leak that's been happening and causing problems in this building over time. We go to the inside, pop open a ceiling tile. I'm not sure if you can quite tell what's going on there, but basically it's a block wall infill underneath a steel structure, that big I-beam with the fireproofing. And you can see might be able to see that little streak of blue. That's the backside of the foam that's on the outside in that brick cavity. Basically, this is from before the era of anybody putting on water control layers, air control layers. So basically, there's a giant air leak at every single one of those beams around the perimeter of the building, causing that air leak that we saw on the outside and causing pipe sweating on the chilled water pipes on the inside on the lower floors. Sometimes you can catch water leaks or water deposition on the outside of a building with an infrared camera, but it's not typically the case. You basically have to catch it at pretty much the right time. It's the right amount of rainfall where basically the whole surface of the wall is not soaked solid. It's, basically see bits and pieces that are wetted, and also the outdoor temperature. The classic time to catch water leaks is when you have outdoor temperature changing, and basically it's going warm to cold, cold to warm, and the wetted parts just respond differently from the dry parts of the building. Who's your guy for infrared shots of architectural landmarks? Here's the Guggenheim building in New York City. You can see that there's these weird little vertical stripes along the spiral of that museum as it's coming down. The reason behind that, you can see that there are these structural fins that hold up the outside wall. One of my colleagues was involved in the retrofit insulation of the walls of the Guggenheim, so basically the walls do not leak as much heat, but those structural fins that still go from inside to outside, those are still obviously the spots where there's no insulation, greater heat loss, warmer surfaces. Now, infrared cameras have come a long way even during my career. Some of you are probably old enough to remember those liquid nitrogen cooled units. That's before my time. When I was starting out, we're talking $5,000 to get this, FLIR camera that'll give you this tiny soda straw view that, 240 by 240 pixels. A few years ago, there were those infrared cameras that plug into an iPhone, super handy. Cost has come down to $400. The current generation, probably I think 200-ish. And what I'm using day to day on my investigations is just a standalone FLIR that doesn't have any of the software hangups. So sometimes some warnings. I've had problems with those little iPhone plugins that basically stuff hangs and you need to restart it. Battery drain, especially if you're walking around in freezing weather on the outside of the building and it's super cold outside, that battery is going to drop down like crazy. Be careful of those little plug-in units. That connector can snap off pretty easily. That's why I had to buy a second camera. Accuracy of the temperatures on the surface might or might not be what you're looking for. There are boatloads of brands and products out there. I use FLIR. I've heard great things about HIK Micro. It's pretty much open season. One thing to remember, though, is infrared cameras show surface temperatures. So you can run into a couple of weird problems with reflections on shiny surfaces. So this was an investigation going around a multifamily building, looking for the sources of the air leakage. Holy cow, there's a giant thermal anomaly on that elevator door. We have a whole lot of hot air leakage coming in there. Nope. That is just the shiny metal door surface, and all that I'm looking at is the infrared reflection of me and my colleague and all of those lights that are overhead. So I definitely recommend, if you're writing up a report trying to explain this to other people, pair up your infrared images with a visual image so to convey what's going on, what's where. And a lot of the time, the current generation superimpose the edges of various surfaces that you see in the visual photo onto the infrared. It's incredibly useful, for instance, if you have 200 infrared shots and you're trying to remember which room did I take this one in. Okay, it's the one that had the Velvet Elvis hanging on the wall. There's always useful information to be found. And every once in a while you run across weird things. This is walking around a client's basement, down at the water heater. Sure, the water heater is warm, the hot water pipe is warm, the cold water pipe is cold, and then what the heck is that behind there? Turns out that the owner's black cat decided that the shelf of the basement was a nice spot to hang out. So basically that explains that weird little thermal anomaly. Moving on from infrared stuff to temperatures, using various types of temperature humidity meters, always useful, both inside the space, maybe inside various parts of the enclosure or the shell. You can range from super fancy ones going up to $1,000 to a really basic temperature and humidity measurement. One thing to remember is that, the temperature measurements are probably going to be pretty solid. Humidity meters, they often flake out. They start to drift over time, and even then, brand new, a lot of the time, you'll take like half a dozen of those little green pens, and they'll be varied by plus or minus 10% humidity. So go ahead and calibrate that against something you know, or figure out whether it's a good one or a bad one. Another point I'd like to emphasize is take a temperature and humidity measurement, but it's also incredibly useful to figure out what the dew point of that measurement is. A dew point is a metric of the absolute amount of moisture in the air. So you can use that to compare, is inside drier than outside, even though inside and outside are at 2 different temperatures. Skip over this a little bit too geeky. So moving on to another subset. Let's go ahead and combine the airflow side of things with heat flow and infrared cameras. So an incredibly useful technique you've probably seen is combining the use of a blower door to pressurize or depressurize a house and using an infrared camera to look for where those air leaks are coming from. So one way you could do it is you pressurize the house, blow air in, air leakage occurs outward through the shell, and you would be looking on the outside of the building for, say, a warm spot in winter where the hot air inside is leaking outward. The problem is that a lot of the time, if you're doing this during the day, the sun is just going to completely overwhelm anything that you can see on an infrared camera, so you might not see much at all. So instead, my go-to technique typically is depressurization, basically ejecting air from the building so that air goes from outside to inside, and you can basically see the cold spots during the winter on the inside of the building. So this just shows, classic examples of what you'd see. One thing to realize, remember, is that infrared cameras show surface temperatures, not air temperatures. Remember, we're looking through the air. It's not showing the air. So all that we're looking at is how those cold jets of air are affecting various surfaces. And you can often see this kind of distinct pattern. I call them jets or plumes. You can see the lousy gasketing under the door, that jet of cold air running across the floorboards, making that pattern. Or in that electrical outlet, you can see the way that it chills the outlet, little jets of air coming out. You often see a star kind of pattern when you're seeing a leaky can light up in the ceiling. Another classic problem, tongue and groove ceilings that span from inside to outside. There is no flipping good way to seal that kind of a condition, and you can see right down every single one of those joints, you have a little jet of air of that cold air getting sucked in from outside. This is a art storage building that was having a massive amount of condensation problems, with millions of dollars of artwork inside. Insulated metal panels, you'd think they're pretty darn airtight. They have that double seal that snaps together. You'd expect that to be pretty solid. So once again, we brought out the big red door of truth, fired it up, and during the summertime, sucking in that hot outside air, a lot of those seams look just fine. You're not seeing any infrared anomaly, but there are other ones where, you too got to have a whole lot of leaks. That's just a fundamental problem. This is a blind seal where they're slamming the panels together. You can't really see whether they've mated completely or not, and some of the seals are great, some of them are not. And you also end up with what you're seeing up at the roof-to-wall interface. That's just where they squirted some foam, tried to call it good enough, and the answer was, nope, it was not good enough. Also, a great technique to use in a finished house is you can see the air leakage from behind the finishes. So what I'm looking at the top photo, that's a vented attic, screaming hot conditions up in the, above the lid, and we turn on the blower door, we suck air down through the ceiling into that wing wall that you see between those two rooms, and it just lights up that wall like crazy. Similar, you look at a cathedral ceiling, turn on the fan, air just gets sucked in from outside, through the ridge vent, down through the fluffy stuff in the bays, and down out inward through the can lights. Those basically cathedral ceilings with a vent chute on top, they're pretty much all a sieve a lot of the time. a lot of the time when I'm doing plan reviews and stuff, clients say like, we got spray foam, we got an awesome air barrier, it's all good. And what I really have to explain to them over and over is that spray foam does a great job of air sealing where it is and does absolutely nothing where it isn't. So that infrared shot shows, spray foam in the stud bays, over in the corner, like, yeah, they didn't shoot the gun in there. And guess what? You got a giant cold air leak coming from that corner. Surprise, no spray foam, no air seal. And just think, all of those wood-to-wood joints, all of those non-spray foam conditions, jack studs, king studs, bottom top plate, those are classic spots where spray foam isn't, and you would get an air leak. Another classic problem is, a lot of windows are installed with a clip system coming to the inside of the opening. Those are just a bear to seal really well, and just about every blower door test I've seen, a lot of them are misses. There's air leaks coming from around them, behind them, etc. The good answers are you either cover the whole thing with a strip of tape, or you bury the whole thing in a line of sealant just to seal every single connection that could happen. Okay, once again, little pressed for time here, so I'm going to skip over this part. It's talking about diagnosing HVAC systems, but apologies to all you HVAC techs out there, but you guys certainly know better about this. So basically, I've been doing a bunch of humidity investigations, and one key thing is looking, is the air conditioner actually dehumidifying? And a lot of the time, the answer is no, not really. They've not set up the system properly, not dialed in the dip switches for the correct airflow adjustment, and basically it's cooling down and meeting set point, but it's not dehumidifying, and that's why we're stuck with 60–70% humidity inside, mold growth on furniture, stuff along those lines. Okay, switching gears away from this air and heat side of things, moving to the water side of things. So water in buildings is one of the most common reason for building problems. It's all about the rain, keeping the rain out of the building shell, controlling it. Then way down the list after rain and liquid water penetration, that's when we're talking about air, and then vapor, handful of problems. It's mostly about the rain coming in as the biggest thing. So when you're talking about rain control in buildings, one first step is deflection. Basically, water shedding details that keep the water off the building from wetting things in general, or wetting surfaces. Then from there, drainage, storage, and exclusion. Those are, for instance, on walls. Drainage would be the way that you would have a rain screen. Water gets through the outside layer, but hits the water control layer, drains down, never enters into the sensitive components. Storage would be the example of, foot-thick brick walls over in New England warehouses. Basically, they soak up the rainwater during the rainy weather. When it's dry, it evaporates out again. No harm, no foul, doesn't get damaged. Exclusion or perfect barrier is we're talking stuff like curtain walls, where if it gets past the plane of that glass, it's gotten into the building. Then on top of that, once the water has gotten in, how well does the wall dry out? The thing is, people often spend a whole lot of time talking about the, drainage and all of these issues, but they're not paying enough attention to the question zero of deflection, keeping that water off of that building to begin with. So, we're talking overhangs, flashings, connection details, drip edges. All of these things are huge for avoiding that risk to begin with. Not putting your wood all the way down to the splash zone of the wall. Architects nowadays seem to be in love with bringing their wood studs all the way down to grade. I tell them, build with rocks in the ground, sticks in the air. Does that make sense? Great. So just a classic example, you guys have probably seen this over and over, missing kick-out flashing. Basically all of that water running off the roof, dumping into that wall. You can see it's a pretty bad obvious sign when there's moss growing on the mortar joints of your brick. We open stuff up on the brick wall, peel back the house wrap. You can see that the OSB is basically turned to mulch, because basically water is getting dumped in there every single rainstorm, wetting the backup wall, causing these kinds of problems. So obviously the answer is a kick-out flashing, basically taking that water that's running off the roof, directing it away from the wall, whether it's sheet metal or a pre-manufactured product like one of these plastic jigs. All of them are great options. When you're looking at a building, looking at how the wetting happens, the one thing to realize is that water does not hit the shell of a building equally. There's varying risks depending on where you are. For instance, the top of the building, that's where you see the most water get deposited. Just walk around, look at a concrete high-rise on the start of a rainstorm, you'll see this exact pattern. It's because the wind is basically whipping that air over the top of the building, carrying the water with it, and that's why you see that deposition up at the parapet. In addition, the corners of the building, once again, the air is wrapping around the sides of that building on the windward side, and that's why you're depositing more of that wind-driven rain over at the corners. It's going to be worse towards the top of the building because the higher you go, the faster the wind speed is. Then you change gears and go to the bottom of the building, and that's where you have splashback, capillary rise, all the stuff at the bottom of the building where you're seeing a whole lot of excessive water showing up there. On top of that, add on the windows. Remember, windows are made of glass. Glass does not soak up water. So basically the wind-driven rain hits the window, runs down, sheds at the sill. That's where you see a whole lot of problems, especially over at the corners where the wind pushes the water one way or the other way, dripping off the edge. We call that mustaching typically. So you can see some of the high-tech tools that I use to demonstrate to builders, hey, you're doing something wrong. Just pour a little bit of water on that windowsill and hey, it's not draining. In fact, it's sitting there because your window guys reverse sloped that sill pan. That's kind of flippin' obvious when they think about it, but if nobody's paying attention, that could be a problem. Draining your water into the wall is never a good thing. So that shows basically you can go ahead and demonstrate, yes, slope the building, slope the pans away, get the water off the building. On top of that, drip edges, like we said, are critical. That water is going to sheet off that window onto the wall below, and you can end up with crazy amounts of water showing up there. So the problem is, if that drip edge is smashed flat against the side of the building, that water is just going to run off and drool right onto the face of the wall like you're seeing in the lower photos. So the key takeaway is, if you have a drip edge detail, be sure to space that off a minimum of ½ an inch so that the water drops free. Even more projection, even better protection. So moisture meters, probably a lot of you have used these things. Showing the yellow one is a pin-based downforce meter. Basically 2 metal pins stick into the wood, measure the electrical resistance across the wood, and that gives you an indication of the moisture content. The other meter there is a Tramex meter. Basically, there are 2 rubber pads, send an electric signal through the substrate, and you can tell the moisture content. The Tramex is even more versatile because it can be used on wood, concrete, drywall, masonry, a whole bunch of substrates. So how would I interpret things? If I'm measuring wood moisture content, if we're talking below 20% moisture content, that's completely well within the safe range. Basically, mold will not grow on wood that's 20% or less. Getting up in the 25, 30-ish% range, that's definitely getting up into the risk range. I would not be surprised to see mold growth. There are probably plenty of buildings that cycle up and down every winter to 25% moisture content. No harm, no foul, they survive it just fine. Up 28, 30, wetter, that's definitely danger territory. We're talking decay fungi actually decaying your structure, causing that level of damage. Really wet wood is kind of obvious. You feel it, it's cold and damp, and basically, if you stick your moisture meter into it, you can actually hear it squish when it goes in. So one thing not to forget though, is that always interpret these moisture content measurements with a little bit of context of temperature. Mold is not going to grow on the food that you store in the freezer, and it's going to grow pretty slowly on the stuff in the fridge. So if the wood is running at high moisture contents only in the middle of winter and then dries out by the time it's getting warmed up in the springtime, hey, it might actually work out all right and survive that type of wintertime wetting. So once again, these capacitance style meters, the one that have the pads, you can measure wood, and the non-wood materials are scored on a 0 to 100 scale. So people often ask me, like, how wet is too wet on these moisture content meters? It's like, concrete doesn't care if it gets wet. It's, we build hydroelectric power plants underwater out of concrete. It really doesn't care. What matters, though, is what the concrete touches. What is it wetting? Is it making your wood floor wiggle all over the place? And what's also incredibly useful is to measure the pattern of wetting that you're seeing. This is just mapping out a basement wall. You can see the above grade part of that basement, 0 out of 100, nice and dry, getting down to the bottom of that wall. Yup, that's the wet spots, and that's where the water is seeping in. That's where the coating is blowing off the wall. Great big surprise. Also, watch out for, if you're doing a drywall measurement, metal can screw up that reading. So you're coming along the wall, you hit the drywall corner bead, and the moisture meter goes crazy. It's just because the capacitance meter is just sensing the metal. So moving on to a case study. This is a building barely a year or two old, and they're reporting all of these problems at the floor. They basically peel back a couple of their rubber-backed floor tiles, and they're seeing all of this black staining on the Advantech. So this part of the building has basically a slab on grade, sleepers with an airspace, subfloor, and then the carpet tile. However, on the other part of the building that's over a basement, basically you can regular wood frame floor, none of that black staining, none of the floor is damaged. Over on the slab on grade portion, people are saying, like, yeah, this floor is actually squishy. We can put our foot through the floor in spots. So we peel up all the carpet tile, and you can see that those black damage patterns match up to the seam. Do moisture content measurements. We're getting 18 to 25%, well up into the risk range on the top of that Advantech. Rip apart the floor even more, and you flip over the Advantech on the bottom of it. That side is even wetter, both confirmed with Delmhorst and Tramex measurements. So the key takeaway that's going on here is that moisture from the slab has been, concrete slabs have a boatload of moisture. Basically, that moisture wanted to evaporate, got to the Advantech, and basically built up there. And the rubber back carpet tile is a perfect vapor barrier, so no moisture got through that. That's why you saw those black stains, and that's why you got that little lighter pattern over at the edges, because the seams of that carpet tile got a little bit of drying. Surprise. Like I said, concrete floors store a massive amount of moisture. This was a forensic job where the wood floor was wiggling all over the place. You drill into the slab, do a humidity measurement, and you're getting 95% on a slab that's been drying 4 to 6 months already. So there is a lot of moisture that can be contained. The answer to that is, if you don't know, haven't done a measurement, you go ahead and put an epoxy coating on it to basically contain that moisture in the slab, or you can build on the top side with a dimple mat and a floating floor, or you can check whether or not there still is a lot of moisture in that slab with various humidity tests. Okay, getting towards the end, we're going to talk about wind-water combination of water and air, or window testing, testing windows for water leakage. So there's the fancy ways of doing this. I'm not sure how many of you work in the commercial space where you do this type of ASTM E1105 test or AMA 502, but basically the way that it works is they hang a big spray rack, water spray rack on the outside of the building. It sprays the outside of the window at a calibrated rate of a certain number of gallons per minute per square foot. And then on the inside of the building, they build this chamber with a plastic cover, suck a vacuum on that, and the intent is basically to simulate the effect of wind-driven rain, where the rain is hitting with the pressure difference of the wind trying to force its way through all of the joints and gaps of the window. This is typically done by specialized contractors that do this work all the time, set up and run the rig. And it's very common for new construction testing as a quality control measure. One thing to realize though, on all of these kind of tests, this is a crazy amount of rain that we're talking about and pressure. So like a typical 8 pound per square foot window test, that's talking 400 pascals. That's a constant 55 mile per hour wind trying to push air through your window with crazy amounts of rain happening at the exact same time. Takeaway is that if your window can survive an AMA 502 test, it's probably going to be just fine in service. In reality, a lot of these leaks happen even without a pressure difference going across that. Basically you can just spray the outside. The thing to realize though is that this kind of a super fancy test is not the only option. This is an example of upper Wisconsin, newly constructed condo buildings, lots of exposure out on the river, and they're having window leaks going all over the place. Looked at a few of the photos they sent and I'm going, uh-oh, mulled windows. For those who don't know, moles are one of the classic problems that you see. So we did the simple version of this. Basically, a guy with a hose making a film of water on the outside. You're not trying to blast water in, you're just making a film. Turn on the blower door, simulate something like a 20 to 30 mile per hour wind, the stuff that they'd be experiencing from day to day. And sure enough, you start seeing water on the inside exactly at the spots where consistent with where it's been leaking before. Also using cobalt chloride paper, that little blue indicator strip, that's really useful because a lot of the time in a photo, it's not going to necessarily capture, is this wet or not? And if you have somebody who's fighting against you, who's saying like, no, that's not water, that's just a reflection. This is a useful tool to confirm, yes, this is water coming in, this is wet. Also, you can stick that cobalt chloride paper into little gaps and stuff, showing like, yeah, we're getting water here at the back of the window. If we've gotten water back here at this line, that means that it'll run sideways and run to the inside if you look at the window profile. Also using a squirt bottle to carefully inject water where you suspect things are going on. Hey, that's another thing where you can show, definitely this leakage path got through this gasket and it shows up on the inside here. So you can also, sometimes you can find water leaks with an infrared camera, sometimes you can't. So this is just one of those slam dunk cases of, yep, they're reporting water leaking through the ceiling, you pull out the infrared camera, yep, there's a giant pool of water that's coming through, that's an open cell spray foam roof, water's pushing its way through. Takeaway, it's the bad flashing detail where that rubber roof hits the wall, basically water's getting in from above, soaks through the assembly, and you see it on the inside. So the reason why you see water leaks on infrared, it could be that it's cold water that's coming in, but on top of that, water is going to evaporate as it dries, cools off a surface, and what you're seeing is that differential temperature of that evaporation cooling off that surface. So here's just another example where I was looking for a water leak. Fancy California construction, glass railing on the outside of the building, and they're having stucco blowing off on that little strip that's underneath that glass railing shoe. How are we going to go ahead and diagnose that? The design of this deck is a tile system where water is shedding off that edge, basically designed to drain behind that shoe detail. Problem is though, this is California during the rainy season. How am I going to find out a water test when the building is already covered with water? What I ended up coming up with is go into the kitchen, turn on the hot water tap, fill up my little squirt bottle, start putting it down behind, or alternately, if you have free reign over the building, you can use a dye or some other type of tracer like that. So what we're showing here is that over on one part where we're not having problems, you drip water off the edge of the deck, yep, that just drains down the face of the stucco, goes away, no harm, no foul. On the other parts of the deck where we're having problems, you pour that water in, nothing is coming out. Basically, there's no good drainage path, water is backing up, forcing its way into the stucco, and then causing those kinds of blow-off drainage problems. So just to wrap up a little bit on this, how I organize these types of investigations. One thing that I want to emphasize is that a lot of the time at the end of the day, you're going to end up with 500 photos on your camera that you're trying to figure out. You are going to go nuts unless you have a good way to track where those photos came from. So go ahead, bits are cheap, take a lot of photos just as breadcrumbs for yourself. Take this photo saying like, okay, we started out on the 5th floor of the building. We started going around the corridors in a clockwise manner. So we're hitting the building, the various units in that pattern, just to give yourself those, recollections of, okay, this is us going into unit 105. Also, when I'm training you guys, I'm just getting too many photos of this kind of a close-up of like half a dozen photos of just this hole in the wall. This tells me nothing. Go ahead, step back, give me a little bit more context. Where are you cutting this hole? Is it near the expansion joint of the building? Is it over where the garage hits? All of those things. That's the kind of thing that's useful to go ahead and walk yourself in when you're trying to remember from these photos. I get asked a lot of the time, borescope cameras, are they good or not? I've been pretty much disappointed when I've used them. Maybe some of you have better luck. So I was looking at a consistent water leak that's happening in this little roof over that punched out bay. And we went ahead, did a tiny hole, put the borescope camera in there, and I'm just seeing fluffy, weird stuff. Really hard to interpret what the heck is going on. What I recommend is go ahead, cut a hole that's big enough to stick your camera in there. Just go ahead, shoot blind, shoots in every single direction, and you'll probably get something that's useful. So this is looking up towards the sheathing of the house. You can see the brick lintel above. That side looks pretty clean. Then looking at the curved roof sheathing over that bay, oh yeah, that might be part of the problem right there. That gives you a far better view of what you're gonna see. So just winding this down, throwing your equipment in a camera case, having for spare batteries, always incredibly critical. So I will go ahead and we'll wrap it up here. Like I said, these slides will be available, and you can catch me later on the trade floor if you have any questions. Thank you very much.